All right. Hey, what's up, everybody? Welcome to chemistry and welcome to Monday, March 24th, I hope. All right. So if you've made it here, you are in the right place. If you are not here, hopefully you'll find it soon. Okay. So just a quick little update. We are officially 40 school days out from the AP tests, and we are going to do this, people. We are going to pass that bad boy. I have 100% faith in you. And to do that, one of the things you have to master is chapter 16, which is all about acids and bases. Okay, so I'm just going to go give you a little quick detail about what you can see with acids, and then we'll kind of talk about the properties of bases. Then we'll look at some definitions, and then we're going to call it a day. Okay, so let's take a look. First off, when you see an acid, you can see that they tend to start with the letter H, right? And this isn't always the case, but this is often the case, is that they contain hydrogen. And if you look at all of these, and we'll talk formulas in a little bit, they all start with H. So a common property of acids is that they tend to start with the letter H. And then, not the letter, the element hydrogen. And then bases, they tend to have OH in them. Okay, so these tend to be like sodium hydroxide. And again, we've used these many times in lab. And so those are important and awesome. Okay, so then let's talk some general properties of acids. Well, first and foremost, acids tend to have a sour taste. And, think about all the things that we eat, and many of these things that we eat, they tend to be sour. So, for example, Sour Patch Kids, delicious, right? Warheads, sour sprays. A lot of the candies we eat, they're rotting our teeth because they're acidic. That's right. So, acids tend to have a sour taste, and pickles, lemons, oranges. Almost all the foods we eat are slightly acidic. Not all of them, but many of them are acidic. Much more of our foods are acidic than they are basic. Okay, so then acids, they change the color of acid-base indicators, and we've done this before too. Remember litmus paper and things like that, and so they change different colors, and so you just have to kind of get familiar with some of the things they change into. So, for example, oftentimes blue litmus paper turns pink in an acid, and vice versa. Pink litmus paper turns blue in a base. If you take an acid plus a metal, you are going to get hydrogen gas. So, for example, if I take HCl, Ca will replace the H in HCl, and you'll get calcium chloride plus hydrogen gas. Of course, I can't break the law. And so there's some acid-base reactions that you might see. And you can see that this goes from 0 charge to +2, so it's oxidized. Remember that? Okay, then you have a base plus an acid, and these will neutralize each other. So this is called a neutralization reaction. Neutralization reaction. These are double replacement. You can see that they're both replacing each other. So you're going to get a salt, Na2SO4 plus H2O. And again, we need to balance it, and you can see there it's balanced. Okay, so if your stomach's upset, oftentimes our stomach has acid in it, so sometimes we'll neutralize some of that acid with like a base. So like calcium carbonate happens to be a base, and it neutralizes some of the acid. So acids also conduct electricity. They are electrolytes, and if you remember that from previous unit, electrolytes are when you put them in water, they produce ions. And so, you get lots and lots of ions with acids. And in fact, the definition we often worked with is an acid, according to Arrhenius, is anything that produces H plus ions in solution. So H plus ions in solution. If you make lots of H plus, you are a very strong acid. All right. So let's get rid of that. Let's move on. Now, one of the things that you have to do when you're describing acids is some acids like you can totally eat, like vinegar is an acid. And if you eat that, it's not a big deal, right? But if you eat HCl, I'm sorry, I need some coffee. Whew. It's cold outside. So it'd be one of those weekend snow days, probably. Okay, so if you put an acid in, like HCl and drink that, you would be in trouble. Whereas vinegar, you're probably okay. So it depends on what type of acid you're working with. So if it's a strong acid, these are the 7 strong. And by the way, you need to memorize these as soon as possible. So make sure you know the 7 strong. They are, I'm going to kind of write them over here. They're HCl, HBr, and HI. Okay, now I say that because these are the order on the periodic table in group 17. So those 3 from group 17, Then you have the ternary acids, HNO3, H2SO4. This is your diprotic. And then we have HClO4 and HClO3. And these make up our 7 strong acids. And what makes them strong is when you put them in water, you get 100% dissociation, which means you get lots and lots of this. Whereas these weak sauce ones at the bottom, they barely produce any H plus. And so what we use for those is, do you remember the double arrow, right? So it means it's a partial reaction. So that's a key thing when describing these things. Okay, so let's keep going. Now, did I go the wrong way? No, I didn't. Okay, so just a quick review on naming of acids. If you are binary, you always use hydro. So binary acid just has 2, so you would say HCl for that. HBr would be hydrobromic, right? It's binary. But if you're ternary, that means you have oxygen in them. So this is chlorate. Chloric means H, so HClO3 is chloric acid. So just remember, you don't use hydro on ternary acids. Chlorus just happens to be one less, so HClO2. So for example, this is sulfuric, again has H, right? This is hydrosulfuric, and this is sulfurous. So that's all 3 of them, right? Binary use hydro, ic, us. Got it? This is from August, by the way, so you've learned that. All right, now let's get into bases. So bases are super cool. All right, they're kind of opposites of acids. What makes them opposite is their structure, but bases tend to taste not sour, right? But they tend to taste bitter. It's funny, I put in bitter taste in Google and the same image came up of the sour face. But regardless, bases don't tend to taste good. So these are bitter. And oftentimes, like unsweetened chocolate, no one wants unsweetened chocolate. It tastes gross, but that's a base. Or baking soda is a base. Or if you've ever accidentally got soap in your mouth, that's a base. It's disgusting. No one's coconut bases and be like, ooh, give me some of that pH of 12. And by the way, they have pH greater than 7. Okay, so that's how you know their bases, their pH is greater than 7. Okay, so keeping that in mind, bases also change the color of acid-base indicators, but they're all different. So we'll get acquainted with them, but like the big ones, like phenolphthalein turns pink in a base. That's the one you need to know. Dilute aqueous solutions of bases feel slippery. So if you've ever seen those, caution when wet, slippery when wet, it's because they're cleaning. A lot of our cleaning agents are bases, and it makes the floor slippery, and people slip and they fall. Or if you've ever seen soap, which hopefully you have, right? It feels slimy, it feels slippery. Or if you're titrating and you get some NaOH on your hands, it feels slippery, okay? So bases react with salts or acids to produce salt and water, just like it before. They're also electrolytes. And then according to Svante Arrhenius, is a base is anything that produces OH minus in solution. That's right. So the acid ion is H plus, the base one is OH minus. Okay? All right, so just some general things on this. So if you are in group 1 or group 2, the soluble ones of group 2. So this would be all of group 1, so Na, K, all those kind of things all the way down. And then in group 2, it's Casabra, or calcium, strontium, and barium. So those are all the strong bases. And this is the same thing. You get a single arrow, 100% dissociation when you put them in water. And weak bases, these tend to be like ammonia or anything else. They tend to have NH2 on them, which we'll talk about. So our group with NH2 or amides, similar to that. These are all weak and they don't 100%. You get the double arrow for these, which just means it's a partial reaction. Okay, we're almost there. Okay, so this is just giving you some examples of the strong acids and strong bases. You can see that some books talk about 6, others talk about 7. Just know, again, generally speaking, these are the main ones that you'll see for strong acids and strong bases. All right, some general properties. So I'm not going to read them all to you, but they change color. They produce, salt and water. They're electrolytes. Yeah, that kind of stuff, which I just went over. But this is a good slide. So earmark this one. Know this one. All right, so getting back, Svante Arrhenius, who's a super stud of chemistry, is like acids are things that produce H plus. And so I am an acid if I make lots and lots of this. Okay, we don't really worry about this very much. It's a spectator ion. Now, we often will see it like this. H plus and H3O plus are kind of synonymous. This is called hydronium. And if you take water and gain an H, it's H3O plus. And so this is the acid one. And likewise, you're a base if you produce lots and lots of OH minus. So for example, if I put NaOH in a base, like why is it a base? Well, you make lots of this when you put it in water. So that is what the definition of an acid is. Okay? Wow, Mr. Woods, so cool. Okay? Now, everybody put a little star by this one. This is an important definition. This is the one that's a little bit different. So certain things act as, this is fun. So you can see I have bird feeders and stuff. Those are woodpeckers that come up to my backyard. So that's why all that pounding, if that's bothering you, it's birds, which I love birds. Okay, so an acid is a proton donor. You'll see this often. And a proton donor, this is something, so if you donate, you're getting rid of. So a proton is basically a hydrogen ion. So let me explain. So H plus, and this is the abbreviation we used. So this tells us how many protons it has. So it's one proton. And if you take 1 minus the charge, it has 0 electrons. And then if you take the mass minus the atomic number, it has 0 neutrons. So it literally is one proton. Okay, so a proton, and when we're talking about this, we are talking about, this is an H plus donor. Okay, so for example, if, can this get rid of an H? Well, yeah, it has one, so it's going to get rid of it. And if it is an acid. So it's subtle, the difference is subtle, but you'll see it in a reaction. And then a base is a proton or H plus acceptor. Remember, acceptors gain. Okay, so this is a loser. This is a gainer. Okay, so keep that in mind as you go. Now I'm going to show you one, and you're going to see it here. So oftentimes you're going to see it like this. So this is going to have an equilibrium system, which means this is an incomplete reaction, right? And you're going to have, much better, very good. Okay, you're going to have, and you're going to look at the before and after. And so you're going to look on the left and see which one has the H, and on the right and which one lost the H. The best way I can do it is show you over here. Okay, so it's going to look like this. You're going to have some equilibrium system. You're going to have some aqueous stuff. You're going to have water because these all occur in water. And then you're going to have to look at the before and after. So I like to look at these. Do you see how they have basically the same atoms involved? Just one is losing an H, one's gaining an H. That's the only difference. Okay, and so you can see that this guy has 3 H's, and over here he's got 4. So he is a gainer. So we look back at our notes and remember that acids are losers, bases are gainers. And so we would call this a base. So that's a Bronsted-Lowry base because it is going to accept an H. So this is the before, this is the after. It's acting as a base because it wants to accept. And then this guy, water here, is an acid. Do you see how it starts with 2 H's and only ends up with 1? So on the left-hand side, this is an acid. That would be the water, and this is a base. Ammonium's a base. Now, since there is a double arrow, this reaction also goes to the left, and so we have to look at it from the opposite direction. So if I'm looking at it from left to right, you can see that this NH4 is losing an H, and so this is what we call an acid, but it's on the right-hand side, so we refer to this as a conjugate acid. So if it's on the right-hand side or the other side of the equation, it's called a conjugate. So NH3, I'm going to write it over here. Hang on. NH3 is the base. Its conjugate acid would be NH4 plus. So base, conjugate acid. And likewise, this is my acid. Remember, it loses one, and this is its conjugate base. So we'll often label it as Cb. Now, when we're down here, take a look at this. So sometimes they'll just ask, all right, what's the conjugate base of this? So if you're a conjugate base, that means that you were an acid, okay? That means, so every acid has a conjugate base. So bases are acceptors. So what is the conjugate base of this? This is going to act as an acid, so it's going to be CO3 minus 2. Every time you lose an H, you lose 1 plus charge, okay? So for example, if I want to know the conjugate base of water, water is acting as an acid, so it would be OH minus. Okay. Now, it is possible, and not always possible, or not with everything, but it's possible that you can be either both. So water can act as an acid or a base. And we say things that can do both. They're called amphoteric, or you often will see it as amphiprotic. Okay. So since they're protons, ampha just means it can do both. Okay. So for example, HCO3 minus, could it give up an H? Absolutely. Could it also gain an H? Actually, it could, right? It could be H2CO3. So since it can do both, it's amphoteric, which means it can be both. But CO2 or CO3 minus 2, it doesn't have an H to give, so it can only accept protons. It can only be HCO3. Okay, so for you to be amphoteric or amphiprotic, you have to have multiple H's. And like water can be H3O plus or OH minus, it can do many things. And likewise, this needs an H before it be amphiprotic. All right, so let's keep going. So you're going to have to do some things like labeling these guys. And this isn't bad. So again, you just look at the before and the after. See how these are the same ones in here? Do you see how this has no H and that gained one? So this is my base, and this is my conjugate acid. It's actually a really important step when figuring these out is just looking at the before and after. Okay, see how it has an extra H? No extra H. So this is my acid. Acids are losers. Let's see if I do it right. Losers. Okay. This would be its conjugate base. And in fact, every acid has a conjugate base. So there'll always be a pair of acid with its conjugate base. And every base has a conjugate acid. That's like a thing. Okay, so let's look at this guy right here. See, there's two, not two. So this is my acid. It's a loser. This would be its conjugate base. And you can see that this gains an H here. So this is my base, and this is my conjugate acid. Water could be both. So we would say it's amphiprotic or amphoteric. Depends on your book. All right, let's keep going. So HPO4, right? Before, after, it's a gainer. So this is a base. This would be its conjugate acid. And then over here, do you see how it loses one? This would be my acid, and this is its conjugate base. They're always opposite. Remember that. And then finally, down here, this is a loser. So this is my acid. This would be its conjugate base. And this would be a base with its conjugate acid. And if you can do that, that's a win for today. All right, almost done. All right, so this is just showing you guys some things, and I just want to mention this. So the net direction of it depends how strong an acid it is. So you can be product favored. So if it is a strong acid, it's going to have a single arrow, and you're going to have, lots of products, and so that would make for a really strong acid. Whereas most of them are weak. Okay, and since that, here's what you have to know. So the strength of the equilibrium system, how far to the right or left, depends how good the acid is in terms of strength. And I'll show you, there's like a chart and there's like KAs that tell you the values. But here's what we need to know. If you are a weak acid, so weak acids have stronger conjugate bases. Stronger conjugate bases. And this is going to be an important part of it. So for example, a weak acid would be like HClO2. Okay, it's not a very strong acid. So it's, when it reacts, it's going to form ClO2 minus, and this is the conjugate base right here. It's just not very, this isn't a very strong acid. This is more basic than it is acidic when I have that. So if it has a weak, it's a strong acid, has weak conjugate bases, and weak acids have strong conjugate bases. This is kind of important right here. And then we're going to get into like Ka and Kb, all that kind of stuff, but it relates to the net direction of it. Another way to look at it is like this, okay? So there's like a chart, and this is in your textbook, and this is like a list of all of the strength. So at the top, these are your strong acids over here. So this is strong. So these are your super strong ones. So if you're a strong acid, so let's talk about HCl. So its conjugate base is Cl minus. We call the conjugate base of a strong acid, since it's so weak, it can't be, it's not even a base, it's called negligible. Negligible means it doesn't make a difference, okay? So it does nothing. And in fact, ocean water is primarily, 55% of it's chloride ion. So this doesn't really do anything, okay? This is a strong acid, its conjugate base is not. Whereas as I get weaker, the strength of the conjugate base becomes stronger. So to figure out which direction these lie, and this could either be to the right, we'll talk about the right, or the left, reactant favored or product favored, you have to compare the two things. Okay, so let's just identify this. So this is a base, and this would be a conjugate acid. And this, if you take a look, is an acid, and this is its conjugate base. And so I'm going to compare which is stronger, this as an water as an acid, or this as an acid, the hydrogen sulfate ion. And we have this little chart, and you can see here's hydrogen sulfate, and all the way at the bottom is water, and water is not the best acid. So since this is strong and this is weak, this direction tends to move this way, which means that when this reaction occurs, there's mostly reactants that are present, not many products, and so that's why it's not a very strong acid. Okay, so it always goes from strong to weak. So when you compare it, you could tell how, what strength it is and which direction it lies. And then how strong is this acid? And, you would say this is negligible, it doesn't do anything. Okay? And I think that's it, people. Let me trash this. Here's some memes for you. Ready? Let's do this. This is funny. So bases be like, I once again am asking for your protons, Bernie. Did someone mix your acid with the base because you're a bit salty today? Ha 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 ha. So if you add acid plus base, you get water. And of course, we're going to drop the base when we titrate a little bit later. And acids are substances which produce hydrogen ions in solution. Bases produce hydroxide. Acids are hydrogen ion donors. Bases are hydrogen ion acceptors. An acid is an electron pair acceptor and a base. This is called the Lewis acid. This is beyond you. All right, I'm going to stop. And of course, we end with Drake. And that, my dear students, is the end of